To find binomial probabilities in R, we use dBinome and pBinome. These are similar to the commands we use for the normal distribution, but because the binomial distribution is discrete, the dBinome command is used to find probabilities rather than the height of a density curve. Recall that dnorm is what we use to draw a normal curve because it gives the height of the curve. But for a continuous distribution, the probability that x equals k equals 0. So we don't distinguish between the probability that x is less than k and the probability that x is less than or equal to k. But for the binomial distribution, dBinome is the probability that x equals k, and we do have to distinguish between these two. Here's an example. An insurance company sells a policy, and now they want to know the probabilities of certain amounts of claims. We have 15 employees, and we're going to assume that they file large dental claims independently of each other. And the probability that any one of them files a claim is 0.3. We can model this as a binomial distribution with n equals 15 and p equals 0.3. To find the probability of exactly 2 claims, use dBinome. dBinome 215.3. pBinome will give us the probability that x is less than or equal to something. Because x can only be an integer, the probability that x is less than 3 is the probability that x is less than or equal to 2. pBinome 215.3. And you can get the same result by adding up the relevant dBinomes. When you're doing these, it can be helpful to draw a graph or table to keep track of the probabilities. The probability that x is greater than or equal to 4 is 1 minus the probability that x is less than 4, because x is either less than 4 or it's not. And that's 1 minus the probability that x is less than or equal to 3, 1 minus pBinome 315.3. When n is big, we can use the normal distribution to get approximately the same answers as we get from the binomial distribution. This is called the normal approximation to the binomial distribution. Here's an example. An analyst thinks that 42% of people support a political candidate. So if you randomly drew someone from the population, there is a 0.42 probability that they would vote for candidate A. And obviously, we're restricting the population to voters in this example. But this analyst thinks that the probability of supporting candidate A is 42%. They poll 200 people, so they take a sample, and only 38% of the sample supports candidate A. Is this an unlikely result? If the true probability that someone votes for candidate A is 0.42, what is the probability that the proportion of a sample of 200 that supports candidate A would only be 0.38? Hopefully soon you'll understand why I'm phrasing the question this way. But we can use the binomial distribution for this. N equals 200, and 38% of 200 is 76. With pBinome, we find that the probability of no more than 76 successes from 200 trials is 0.1411. And the reason we're using pBinome instead of dBinome here is that the probability of exactly 76 yeses is really low, and it's deceptively low because the question we really care about is whether the population proportion is lower than 0.42. A sample proportion of 0.38 suggests that it is lower, and if we got a sample of 70 out of 200, or 50 out of 200, or 20 out of 200, that would make us think the population proportion is less than 0.42 as well. That's why we look for the probability that the number of successes is less than or equal to 76. That's how we would answer the question with the binomial distribution. Here it is with the normal. If you encode success as 1 and failure as 0, then the proportion of successes is the sample mean. Here's what I mean by that. Say you have a sample of 4. If yes equals 1 and no equals 0, this is and the sample mean is 1/2, and that is the proportion of yeses. The sum of all the values in the data is the count of successes. Divide that by the sample size and you have a sample mean. Because a sample proportion is a sample mean, it has the same properties as a sample mean. Namely, it's governed by the central limit theorem, which says that as n gets big, the sample proportion will have a normal distribution. The sample proportion is written p hat. The hat is to distinguish it from the population proportion, which is p. So the central limits theorem says that this thing is normal with some mean and standard deviation divided by the square root of n, where mu and sigma come from the population. Now remember earlier in the lecture I said that mu equals np and sigma equals the square root of np times 1 minus p. So these are for the counts. So if the count has mean np, then the count divided by n will have mean p. And if the count has standard deviation this, then the count divided by n will have standard deviation this. And so the central limit theorem tells us that the sample proportion follows a normal distribution that looks like this, where P is the population proportion. We know N and P. We plug them into the formula from the central limit theorem, and what we get is that the sample proportion follows this normal distribution. We use p-norm to find the probability of getting a sample proportion less than or equal to 0.38, and it's 0.126, which is pretty close to what we got from the binomial distribution. This is only an approximation though, and this will get better with bigger n. Here's the same scenario with n equals 1,000. Now, the probability of getting a sample proportion of 0.38 or less when the true proportion is 0.42 is 0.00552 by the binomial distribution and 0.005191 according to the normal approximation. Notice that these methods use different statistics. For the binomial distribution, the statistic, the number we calculate from the sample, is the count. For the normal approximation, the statistic is the proportion.